So today we're going to continue our discussion on series and parallel circuit behavior and kind of combine the two of those in a couple examples. Here we're looking at the idea that the source voltage is divided proportionally among the series resistors. This is a series configuration. Since this voltage is divided proportionally, we can see here that this particular resistor, because of this relationship here, this is twice as large as this one. That means that this voltage is going to be twice the voltage of this one. And we see that this one is going to be 3 times this. So we can use that voltage divider principle and say that this is 2 out of a total of 12, or 1/6. So that means we would get 1/6 of this voltage. But we don't have this voltage at this point, so that's not really going to help us. So what we do have is the total current for the circuit. And since this current's flowing here, we know that it's a continuous loop, nothing's lost, that there's 2 amps flowing through this one, it's flowing through this one, and it's flowing through this one. And as it flows through these resistors, it kind of backs up like water going through a culvert pipe, and a voltage develops across this. It's the same as the example where I have water flowing and I put a stick or a boat oar in the water, and you feel that force that's created. That force is voltage, and we can calculate that using Ohm's law. This is saying that this total, and this total, even though it's divided proportionally, if you add them all up, it equals this. Because I have 2 amps flowing through this one, that develops 4 volts. And 2 amps going through 4 ohms, 2 times 4, 8. 2 times 6 is 12. And you see that, as we talked about, this is twice as much as this. This one's 3 times as much as this. And when you add those, V1, V2, and V3 together, you get V total 24 volts. So if we only had 24 volts and not the current, then we could have done a couple things. We could have used the voltage divider principle and used that proportionality. Or maybe, since we know that in a series circuit, the total resistance is the sum of each one, we could have calculated the total resistance and using Ohm's law divided it into the voltage, and we could have got this current. This is saying kind of the opposite of this. If you start out with your total and then you start subtracting these individual ones, by the time you're done, you're going to end up with 0. And yes, 24 minus 4 minus 8 minus 12 leaves nothing. All right, the current law. This is saying that the total current leaving the source is equal to all the currents in all the branches combined. So this current is going to also divide inversely proportional. By inversely proportional, I mean that the greater amount of current is going to the smallest resistance. So think about that. The smallest resistance to flow, the smaller the resistance you have, the more current can flow. So that stands to reason that your larger resistance is going to restrict the current the most. Therefore, it'll get the least current. So the current that leaves here divides inversely proportional, and then they join together. So I1, I2, and I3 total current. So in this case, we're seeing 22 amps, and we see this proportionality. We see this going. And notice here, this has half the resistance of this, so that means it gets twice the amount of current. We could have calculated these currents individually by saying 24, using Ohm's law. 24 is across all of these because these are in parallel. 24 across here. So using Ohm's law, 24 divided by 2 is 12 amps. 24 divided by 4 is 6 amps. 24 divided by 6 is 4 amps. I've got that current here. If we didn't know this current and use proportionality, we could have calculated the individual currents knowing that they all combine to equal this. This is saying whatever's coming in has to equal what's going out. So a battery doesn't know what's out there in the circuit. So here's a battery. It doesn't know what's out here, how it's combined. All it does is feel the effects of the combined resistances. And Ohm's law says that that combined resistance in opposition to the force of the voltage results in a certain amount of current flow. So I think if you were to imagine that that it's the combination of the resistances that the battery senses and the current results from that, it really gets down to how those resistances are combined. We know that a series resistances are combined by just adding them together, but we also know that parallel resistances have to be combined in one of those other methods we talked about. And when you have a more complex circuit like this one, where it's a combination of series and parallel, you have to make sure that you combine them in the appropriate way. But in any event, no matter how complex the circuit, it can be reduced to an equivalent circuit. Again, this represents all the resistances that are out there in whatever configuration they're in. The source responds to that or senses that, and the amount of current that flows is simply Ohm's law, this divided by this. So how do we combine those? Typically what we want to do is start, if this is where the battery would be located in this circuit, typically we want to go away from the battery and start working this way. In this case, I've got a 60 and I'm moving this way. The next one that it's combined with is this 30 ohm resistor. This is combined with this. How do we combine these? Well, it depends on how they're connected. Are they connected in series? No, because they're connected at 2 points. Current doesn't flow into one and directly into the other. So that means that these are in parallel because of these branch points. So I've got to combine these in parallel, and we can use the couple different methods. We can use the reciprocals of the resistance to get conductance and then get the reciprocal of that. Or since I just have two of them, I'm going to use the product over sum. So I'm going to multiply 30 by 60 product and get 180, 1800. And then I'm going to divide it by the sum. 30 plus 60 is 90. And I'll get the 20 ohms. Now I'll go the next step. Now that I've combined these, the next step in this finding out the equivalent resistance is to take this one and combine it with the next one. Well, the next one is this 40 ohm resistor, and it's connected in series, so I simply just add this. So in this case, this circuit can be reduced to its equivalent circuit with a total resistance of 60 ohms. In this example, I have a 5 ohm and a 20 ohm that are clearly in parallel, and they should be combined by that. So product over sum again, 5 times 20 is 100, divided by the sum of these, which is 25. This is going to have a resistance equal to 4 ohms. Now, going the next step, I combine this with this, and we see that It's in series, so these are just additive. The total resistance, the equivalent resistance for this circuit then is 10 ohms. Finding currents. All right, what do we have here? What's provided? I have 120 volts. I want to find out the total current, and I want to find out I3, this current. Well, I know this. If I have a certain amount of current that's leaving the source, my total current, and it's coming back this way, it had to flow through this. So whatever left here got to this point, and it divided inversely proportional, but I don't even have to worry about that because I know that it comes back together again. Whatever left is remerged here and flows through this. So what I'm saying is, if I find out IT, I3 is exactly the same. They're saying that from the last example that we calculated, the total resistance is 10 ohms. This is from the previous example where we resolved this and we had resistance given. So if the total resistance is 10 ohms for this circuit, then the total current is simply, using Ohm's law, 120 divided by 10 is 12 amps. So 12 amps is leaving here. It splits inversely proportional, rejoins together, and that total 12 amps flows through there. Finding voltages. So we found the current. We first found the resistance for that circuit. Now we found the current. Now let's get the individual voltages. The way I would look at this, so I have 120, but it's not all across this. Some of this 120 got divided here. These two are in parallel. They can be combined into an equivalent resistance that would be in series with this, and then that would mean this 120 volts gets divided among this and this. All right, but what information do we have now? I've got 120 volts. I don't know this, so I don't know the proportionality, but I have this 12 amps. So 12 amps going through 6 ohms will give me that 72 volts. So there's 72 volts across this. Now, I know that this voltage that's across this parallel connection and this voltage has to equal 120. So I can figure out what this is by subtracting this 72 from 120. And that gives us 48 volts across this parallel connection. Because these are both in parallel, V1 and V2 are the same. But what about these currents? Finding this, we're figuring out all the aspects of the same circuit. So I've got 12 amps, and they give us ohms here. I could do two things. I could see this proportionality and know that I've got a total of 25 parts, and 4/25 goes this way and 1/25 goes this way, and I can use this current that's going in here to figure this out, knowing that the larger amount of current is going to go this way through the smallest resistance. But it's a little easier than that because we already have determined that I have 48 volts across both of these. So if I just divide 48 by 12, Ohm's law, I know the current flowing this way, and I know the current flowing this way. I could have subtracted this current from 12 amps, and then that would have given me how much current was left to flow this way. At this point, you can solve this problem using multiple different ways because you have so many factors available that you can fit it into various forms of Ohm's law. Whatever way makes the most sense for you, whatever way seems to be most intuitive and common sense, that's the right way. Now, completing the chart to find power. Well, we can find power in multiple ways. For this circuit, we've found all of this through the previous processes. Now to find power, I can use V squared divided by R. I can use I squared times R. I can use V times I. So any of those will give me the same answers for each of those. All right, finding voltages. What I have here is 24 volts across this parallel connection. I have 12 volts across this parallel connection. That tells me that this voltage and this voltage can be added together to give me this voltage. So this voltage is 36 volts. Because these are in parallel, V3 is the same as V4, V1 is the same as V2. Finding currents. 5 milliamps leaving the source, which means there's 5 milliamps returning. And that 5 milliamps is going to get split inversely proportional. And it was started out as 5, and there's more than half of it going this way. So that tells me right there that this resistor is smaller than this one. But more specifically, I can see that I start out with 5, and I have 3 going this way. What has to be going this way is the other 2. So 2's going this way, 3's going this way. They combine again and enter into here. I've got 1.5 going in here. So the rest of it has to be going this way. And then it recombines and goes back. All right, so here we have the chart, but we don't have the resistances. But it's easy enough to find out because R is equal to V divided by I. We simply divide the current into the voltage for each of those resistors, and we'll get the resistance. And completing the chart to find power using any of the power formulas. Now, let's see what we have here. I can figure up my total, finding RT is what they're asking for. So I've got 5 and 7 that's in series. So essentially I can replace this with a 12 ohm resistor. I've got a 1 and a 3K, so I can replace these two with a single 4K resistor. So now I have 4K in parallel with 12K, and I can use my product over sum to get the total circuit resistance. 12K, 4K. Total resistance, this in parallel with this, 3K. Now, taking the same equivalent circuit, R total is equal to 3K. We want to find the current. So VT is 60 volts. The total current is simply going to be the 60 volts divided by the 3K. 20 milliamps. Here we're calculating 60 volts across this one, 60 volts across this one, and the current V divided by R gives us these currents. And you see that we start out with 20 milliamps and it divides and remerges. All right, the voltage. Calculating the voltage. Should be easy enough because V equals I times R. So we'll just do this would be 25, 15, 35, 45. And completing the chart to find the power that's dissipated in each of those resistors, we get these values. All right, here we have something a little bit different. We're looking now at failures. This is a circuit failure. In this particular case, I have an open circuit in R1. How does that affect the rest of the circuit's operation? Well, we'll start out looking that current, total current, is going to flow this way. It's going to get to this point, and R1 is not going to happen. It's an open circuit, a dead end, the drawbridge is up, no traffic can move. This I1 current is going to be 0. I2 current is going to flow and come down here, and the same current that flowed this way is going to go through this way. So even though I originally had a parallel circuit here, the fact that this opened up, it's out of the picture, has turned this into a series connection with this resistor in series with this resistor. So 26 ohms is the total resistance for the circuit now, which means the current is going to be 120 divided by 26 ohms. And whatever current's flowing as a result of that, the total current, flows through this one and this one. So the resistance of this now, infinite. Twenty-sixth, 20 plus 6, the current, 120 divided by 26, flows through R2 and R3. Nothing's flowing through R1. And the voltages are calculated by using 6 times 4.62, 20 times 4.62. And we see that the voltage is across here. That same voltage, because this is still in parallel, even though this is an open circuit, that same force is here. And remember we said that an open circuit, that the max voltage is there. Now let's make a distinction that this voltage that's across here, all of this voltage that's present is across here. But it's not the max of the circuit, because the max of the circuit is 120. So you can't assume that 120 volts is across here, because 120 volts wasn't available here. But what is available is 92.4 volts, and that's what you'll see across these 2 points, because this point is the same as the points on this resistor. No power because there's no current. I squared times R. I squared is 0, so 0 times anything is 0. And think you can't have power. You have to have current has to flow through your load or through an element to do any kind of work, and that's where power is coming from. So if there's no current flowing, there's no power that can be there. In this case, I have a short. How does a short change characteristics of a circuit? Well, in this case, I have a certain amount of current that's leaving the source, and it's going to split because there's a path here. There's a path to go through, and then recombine and return this way. So in this case, I have 5 plus 7. These two can be combined. They're in series. I'll combine them into 12. And here, this turns into 0 ohms. So I have 0 plus 3. So in this particular case, I have 3 combined with 0, or 3 So I have 3 in parallel with 12. And that's how I would calculate the current. By getting this equivalent resistance, dividing that into the total voltage to get the current that's leaving here. It's 25 milliamps. Now I have 60 volts across this, and I know that it's 12 volts, so I can figure my current is 5 amps. And here I have 60 volts across 3. I can come up with a current here as 20. And again, you see that if you calculate one of these currents and you know what the total current was, this is whatever's left. You can just subtract this from the total to get this. Again, do it the way that seems the easiest, what comes to your mind the easiest. That's the right way to do it. And then using the power formulas to complete this table.